In every direction you look, the universe seems packed with galaxies. But scientists found something impossible: a bubble of nearly empty space, 2 billion light-years wide, and we are living deep inside it. We call it the local hole. It rains no metal and hides no monster, but it may be doing something stranger. It could be bending the numbers we use to measure the entire universe. Tonight, we travel from a blank patch of sky first spotted in 1981 into a void so large it breaks the rules of cosmic chance, and straight into a crisis scientists call the Hubble tension, a gap between two measurements of the universe's expansion that should never disagree. If you're new here, hit subscribe, because what we uncover next might change how you see everything above your head. Prepare yourselves. We begin. Look up on a clear night, far from city lights, and the sky looks crowded. Thousands of stars, a pale smear of the Milky Way. It feels like space is packed edge to edge with light. That feeling is wrong. Stars sit so far apart that if you shrank the sun down to the size of a marble, the nearest star would be another marble more than 4,000 miles away, roughly the distance from New York to London. Between those marbles, there is nothing. No air, no dust you could touch, no sound at all. Space is not a crowded room. It is mostly a silent, empty ocean, with tiny islands of light scattered impossibly far apart. Now zoom out even further. Stop thinking about stars. Start thinking about galaxies, each one home to hundreds of billions of stars like our sun. Even at that scale, the same pattern repeats. Galaxies gather into clusters, clusters link into long glowing filaments, and between those filaments sit enormous gaps with almost nothing in them at all. Astronomers call these gaps voids. They are not rare. They are not small. Voids make up most of the volume of the observable universe. If you built a giant-scale model of the cosmos, most of it would be empty rooms, with galaxies clinging to the walls and corners like furniture pushed against the edges. For most of history, nobody knew this. Ancient astronomers assumed the stars were fixed on a distant crystal sphere, evenly placed, evenly spaced. Even 100 years ago, scientists pictured the universe as roughly uniform, the same density of galaxies no matter where you looked. It took powerful telescopes and years of patient mapping to reveal the truth. The universe has structure. It has walls and bubbles, threads and gaps, like a cosmic sponge stretched across billions of light years. That discovery raised a new question. If galaxies cluster in some places and vanish in others, where do we sit? Are we tucked inside a busy, crowded thread of galaxies, or are we drifting somewhere closer to one of the empty gaps? For a long time, scientists assumed we lived in an average spot, a typical neighborhood, nothing special. That assumption felt safe. It matched simple thinking. Earth is not the center of anything, so surely our galaxy is not special either. But comfortable assumptions have a habit of falling apart under careful observation. Astronomers pointed larger telescopes at deeper patches of sky, counting galaxies with painstaking precision, patch by patch, degree by degree. And in one particular direction, in one particular survey, something odd showed up. A patch of sky that should have held thousands of galaxies held far fewer than expected. At first, scientists suspected a mistake, bad equipment, a miscount, a blind spot in the data. They checked again. The numbers held. A section of the universe, absolutely enormous by any human measure, appeared to be missing most of its galaxies. No equipment glitch caused it. No shadow blocked the view. It was a real, physical gap in the structure of the cosmos, sitting right where scientists expected to find ordinary space packed with light. This discovery would eventually pull scientists toward a question stranger than a single empty patch of sky: the question of whether we ourselves might be living inside one. Every big discovery starts with someone doing boring, careful work. Nobody sets out looking for a hole in the universe. They set out to count galaxies, one by one, patch by patch, night after night. In 1981, astronomer Robert Kirshner was mapping the positions of galaxies in a small patch of sky in the constellation Boötes, the herdsman. His team was not hunting for anything unusual. They were doing careful, routine work, measuring redshifts, calculating distances, plotting galaxies onto a three-dimensional map, like pins on a corkboard. Then a section of that corkboard came back almost bare. Where the team expected to see galaxy after galaxy, they found almost nothing. Just a handful of faint smudges scattered across a region of space so large it would take a beam of light 330 million years to cross it. Picture the distance from New York to Los Angeles. Then multiply that trip by roughly 50 million. That is the emptiness we are talking about. Kirshner's team checked their equipment. They rechecked their calculations. Nothing was broken. The gap was real. They called it the Boötes Void. Later, someone nicknamed it the Great Nothing, and the name stuck because it fit so well. Inside a region big enough to swallow hundreds of thousands of galaxy clusters, astronomers found roughly 60 galaxies. For comparison, an average region that size should hold closer to 10,000. It was as if someone had reached into the universe and scooped out almost everything, leaving only scraps behind. Naturally, people asked the obvious question: could this be a black hole? The answer is no, and the reason is simple. Black holes are small, dense points that trap light. The Boötes Void is the opposite. It is enormous and nearly empty, letting light pass through freely. It is not a wound in space. It is closer to a canyon carved out of the cosmic landscape, a place where galaxies simply fail to form in large numbers. Scientists were confused in a way that mattered well beyond simple surprise. Standard models of the universe, built on decades of careful physics, predicted that matter should clump together fairly evenly across large enough scales. Small voids, sure, gaps here and there, expected. But a void this size, this empty, sitting in front of astronomers with no obvious explanation, did not fit neatly into the math. For years, the Boötes Void stood alone, an oddity, a curiosity mentioned in textbooks as the biggest known gap in the universe. Astronomers assumed it was a strange exception, a rare roll of cosmic dice, and moved on to study other things. Confirmed observation, not theory. The data was solid. What it meant was still a mystery. Some scientists tried to picture what it would be like to actually stand inside the Boötes Void on some imaginary planet orbiting one of its 60 lonely galaxies. Looking up at night, that planet's sky would show almost nothing. Just a handful of faint smudges scattered across an otherwise black dome, a view lonelier than anything a human has ever witnessed from Earth. But science rarely leaves a mystery alone for long. Decades later, better telescopes and wider surveys would begin finding other gaps, bigger surveys covering bigger patches of sky. And slowly, a strange pattern would emerge, one that would eventually point scientists toward a discovery close enough to touch. Not somewhere distant in the depths of Boötes, somewhere shockingly close to home. Here's the problem the Boötes Void created for scientists. In a universe built mostly by chance, small clumps and small gaps are normal. Flip a coin 1,000 times, and you will get short streaks of heads or tails just by luck. But flip that coin 1,000,000 times and get 500 heads in a row, and something else is going on. The Boötes Void looked like that kind of streak. Too big, too empty, too unlikely to be a simple accident of random clumping. Cosmologists rely on a number called the density fluctuation, essentially a measure of how lumpy or smooth the early universe was. From that number, scientists can calculate how likely it is to find a void of a certain size, purely by chance, across the whole universe. Small voids. Common, expected, no problem. Voids the size of Boötes. Possible, but rare enough to raise eyebrows. Then things got stranger. As telescopes improved through the 1990s and 2000s, astronomers built bigger three-dimensional maps of galaxies, plotting hundreds of thousands of positions instead of a few thousand. Instead of finding one freak gap and calling it a day, they started finding void after void, scattered across the cosmic web like holes in Swiss cheese. Voids, it turned out, are common. In fact, when astronomers add up all the empty space between galaxy filaments, voids make up close to 90% of the universe's total volume. That reframed everything. The Boötes void was not some bizarre one-in-a-billion outlier. It was an extreme example of something completely ordinary: cosmic architecture. The universe naturally organizes itself into filaments, walls, and voids. The same way water naturally forms bubbles inside boiling foam. Gravity pulls matter along invisible threads, leaving the space between those threads stretched thin and empty. Picture a sponge pulled straight from the kitchen sink. Most of its volume is hollow, riddled with holes, yet it still holds its shape because of the thin walls running between those holes. The universe behaves the same way on a scale almost too large to imagine. Threads of galaxies forming the walls, and voids like Boötes filling in the empty holes between them. But knowing voids are common did not answer the harder question. If galaxies cluster into filaments and empty pockets stretch between them, then some galaxies must sit closer to the crowded threads, and some must sit closer to the empty pockets. Every single galaxy has an address in this cosmic map. Every star, every planet, every person reading this sentence lives somewhere specific inside that structure. So astronomers turned the telescope, in a sense, back toward home. If voids like Boötes exist, scattered across billions of light years, was there any chance one might be sitting closer than anyone expected? Not far off in Boötes, tens of millions of light years away, somewhere practically in our own backyard. That question sounds simple, but answering it meant redoing an enormous amount of careful work, measuring distances to millions of galaxies, and correcting for dust blocking the view. That question would lead scientists to results even they did not expect, and it would start with a discovery that had actually been sitting quietly in the data for years, waiting to be noticed. Long before the biggest discovery, there was a smaller clue. In the 1980s, astronomer Brent Tully was mapping galaxies in our cosmic neighborhood, the region within about 65 million light-years of Earth. Most directions were full of galaxies, some near, some far, all roughly where you'd expect. But in one direction, stretching across a huge patch of sky, Tully found almost nothing, a gap, right at our doorstep. He named it the local void. It sits close enough that its edge grazes the outer boundary of our own galactic neighborhood, the local group, which contains the Milky Way, Andromeda, and around 100 smaller galaxies. Picture a mostly empty parking lot sitting directly next to your house. That is roughly how close the local void sits to us, on a cosmic scale. At first, this seemed like a fun curiosity, a gap near home, nothing more. But then astronomers noticed something else, something that had nothing to do with counting galaxies directly. They noticed motion. Our entire local group of galaxies, including the Milky Way, is not sitting still. We are moving through space at roughly 1.3 million miles per hour, being pulled towards something. Astronomers nicknamed the mystery destination the Great Attractor, a region of unusually dense galaxy clusters pulling everything nearby toward it, like a drain pulling water. Here is the part that connects the dots. Gravity pulls toward dense regions, and it also pushes away from empty ones. When one side of your neighborhood has significantly less mass than the other, gravity from the denser side wins, and everything gets tugged in that direction. Our motion toward the Great Attractor involves more than a simple pull from one side. Scientists began to suspect we were also being pushed from the other side, from the empty region behind us, from the local void. That idea might sound small, almost technical. It carries real weight. If the local void really is nudging our galaxy through space, it means we are not simply floating in some average, unremarkable spot. It means the empty region behind us actively shapes our motion, our position, our entire trajectory through the cosmos. Empty space, doing something, shaping the flow of galaxies around it, the same way a hole in a crowded room quietly reorganizes how everyone else stands. Think about walking through a packed train station. You rarely walk in a straight line. You drift around the thick clusters of people, and you drift faster through the open patches, pulled along by the shape of the crowd itself, even though nobody touches you directly. Astronomers were beginning to suspect our entire galaxy moves the same way, drifting through the cosmos, guided as much by the empty patch behind us as by the crowded region ahead. This was the first thread. A gap near home, a mysterious motion, a hint that maybe, just maybe, we were not living in the safe, average middle of the universe that everyone assumed. But this was still just a local curiosity, confined to our tiny corner of space, 65 million light-years wide at most. Nobody yet suspected how much bigger the true picture would turn out to be. That answer was still decades away. Hidden in survey data nobody had fully connected yet. Fast forward to the 2000s. Astronomers had far better tools than Tully ever had. Infrared telescopes that could see through dust, X-ray detectors that could spot hot gas, radio surveys that could map galaxies invisible to ordinary optical telescopes. Different teams, using completely different instruments, started counting galaxies across huge stretches of sky, far beyond the small local patch Tully had studied decades earlier. And a strange pattern kept showing up, repeating across survey after survey, across different wavelengths of light, using different telescopes built by different countries. In every direction, scientists looked out to several 100 million light-years. There were consistently fewer galaxies than the standard model of the universe predicted. Fewer normal galaxies in visible light, fewer infrared sources, fewer X-ray emitting galaxy clusters, fewer radio sources. This mattered enormously because it ruled out the easiest explanation. If only one survey, using one type of telescope, had found a deficit, scientists could blame the instrument. Maybe the telescope was less sensitive in that direction. Maybe cosmic dust was blocking the view. But when telescopes measuring completely different kinds of light, sensitive to completely different kinds of interference, all agree that galaxies are missing in the same region of sky, the explanation cannot be a broken instrument. It has to be real. It is a bit like asking 5 witnesses, each standing in a different spot, each using a different pair of glasses, to describe the same street corner. If all 5, independently, describe the same missing building, you stop suspecting their eyesight and start suspecting the building really is gone. By around 2013, astronomers Ryan Keenan, Amy Barger, and Lennox Cowie pulled these threads together into a single, staggering conclusion. The deficit was not confined to a small patch near the local void that Tully had found. It stretched across a region measuring roughly 2 billion light-years across. 2 billion, not million, billion. A void so large that comparing it to the Boötes void, once considered the biggest hole in the universe, would be like comparing a swimming pool to an ocean. They named it the Keenan-Barger-Cowie void, later shortened by other scientists to the KBC void, though many simply call it the local hole. And here is the detail that changes everything about this story. This void surrounds us, rather than sitting as some distant structure discovered by pointing a telescope far across the universe. Its edges are drawn in every direction from where we stand. We are not looking at the KBC void from outside, the way we viewed Boötes decades earlier. We are, as far as the data shows, sitting somewhere inside it. For the first time, scientists were studying the hole they lived in, rather than simply a hole in space somewhere out there. That single shift in perspective changed everything about how the story felt. A void discovered far away is a fascinating fact. A void discovered, wrapped entirely around your own galaxy, is something closer to finding out the house you grew up in was built on top of a hidden cave nobody had ever mapped. And once astronomers accepted that starting point, an unsettling question followed immediately. If we are inside this void, exactly how deep inside are we? Are we near a wall, close to the edge, or are we sitting somewhere in the emptiest part, as far from any dense structure as it is possible to be? Picture the biggest stadium you can imagine, packed edge to edge with a screaming crowd. Now, imagine that instead of standing near the exits or close to the field, you are standing dead center in a patch of open concrete with almost nobody around you for what feels like miles. That is roughly the position scientists now believe we occupy inside the KBC void, not near the crowded edge, closer to the empty core. This detail matters more than it might first appear. If Earth sat just inside the boundary of the void, close to the denser galaxy filaments outside it, the effects on us would be small. A minor local quirk, interesting to specialists, forgettable to everyone else, but sitting deep inside an underdense region changes the picture completely. The farther you are from the crowded outer walls, the stronger and more consistent the emptiness around you becomes in every direction. Astronomers worked out our approximate position using the same galaxy count surveys that first revealed the void's existence, checking how the density of matter changes as you move outward from our galaxy in every direction across the sky. The results consistently placed us well inside the boundary, not hugging the edge like a nervous swimmer near the shallow end of a pool. Astronomers estimate we sit roughly in the central third of the KBC void, closer to its heart than its rim. That means for hundreds of millions of light years, in almost every direction, the density of galaxies around us stays consistently, measurably lower than the universe's overall average. It is not a small dip in one corner of the sky. It surrounds us like a shell. Why does this matter beyond simple geography? Because gravity does not care about human curiosity. It responds directly to how much mass sits nearby and in which direction. If the region around us has significantly less mass than a typical region the same size, that missing mass changes how everything nearby moves, drifts, and expands. Galaxies at the edges of an underdense region feel a gravitational pull toward the denser walls surrounding it, the same way water at the center of a shallow bowl slowly drains toward the deeper edges. This creates something astronomers call an outflow. Imagine standing in the center of that huge empty stadium again, except this time, the ground itself is slowly tilting outward in every direction, gently sliding everyone standing near you toward the distant seats. Nobody feels a sudden shove. It happens slowly, gradually, over unimaginable stretches of time. But the motion is real, measurable, and, as we are about to see, deeply important for one of the biggest unsolved puzzles in modern cosmology. Astronomers have actually measured hints of this motion directly, tracking how nearby galaxy clusters drift relative to each other. The direction of that drift lines up with what an outflow from an underdense region should look like, matter easing away from the empty core, gathering speed as it approaches the crowded walls in the distance. It is a subtle signal, buried in a sea of ordinary cosmic motion, but subtle is not the same as absent. Before diving into that puzzle, scientists needed one more piece of the picture, exactly how empty this region really is. Number in hand, or the effect stays theoretical, and when scientists finally calculated that number, it turned out to be far more dramatic than anyone expected walking into the analysis. Numbers alone rarely tell a story, but this one does. When astronomers calculated the density of matter inside the KBC void compared to the universe's overall average, they found something startling. The region immediately around us, stretching out to roughly 1 billion light-years, contains only about half the matter you would expect in a typical patch of space that size. Half, not a 10% dip, not a rounding error buried in the noise of imperfect measurements. Roughly half of the galaxies, half of the gas, half of the mass that should, by the standard rules of cosmology, be filling the space around our galaxy. Picture a school bus built to carry 60 students, driving around with only 30 on board, every single day, for years. That persistent, structural absence is what scientists are describing. Now stretch that missing half across a region so large that light itself needs roughly 1 billion years just to cross from one edge to the other. Surveys checked whether a few overlooked galaxies hiding behind cosmic dust might fill that gap, scanning in infrared light capable of seeing through the thickest dust clouds in our galaxy's way. The missing galaxies simply are not there. This is where trust signals matter. The existence of the void itself, the raw fact that galaxy counts drop in this region, is confirmed by multiple independent surveys using different telescopes and different wavelengths of light. That part is solid ground. But the precise depth of the void, exactly how much matter is missing and exactly how far the emptiness extends, still carries real uncertainty. Different research teams, using different methods, have calculated numbers that range from a modest 20% deficit out to nearly the 50% figure. Science treats this as an active area of measurement, not a locked-in fact. This kind of range is normal in frontier research. It does not mean anyone is guessing wildly. Each team is measuring something slightly different survey depths, different corrections for dust, different statistical methods for separating a true void from ordinary cosmic noise. Narrowing that range down to a single trusted figure remains one of the active goals driving newer, more ambitious surveys forward. Still, even the more cautious estimates describe something extraordinary. Whether the true number sits closer to 20% or 50%, either figure describes a region of space significantly emptier than a random patch of universe has any right to be, according to the standard model most cosmologists use to describe how matter should clump together after the Big Bang. And this is where the story shifts from curious to consequential. An empty region, sitting quietly in space, doing nothing but existing, would simply be an interesting geological feature of the cosmos, worth a mention in an astronomy textbook and little else. But this void is not doing nothing. Its missing mass creates a gravitational imbalance, an imbalance strong enough to influence how fast nearby galaxies appear to be moving away from us. And that detail connects directly to one of the strangest unsolved problems in physics today: a disagreement between two different ways of measuring how fast the entire universe is expanding. A disagreement that has puzzled cosmologists for over a decade, resisted every attempted explanation, and just might, according to a growing group of scientists, trace back to the empty region we happen to call home. Before we can understand how an empty patch of space might distort a measurement, we need to understand the measurement itself and why it has become one of the most argued about numbers in all of science. Here's something almost every physics class eventually mentions. The universe is expanding, space itself is stretching, carrying galaxies farther apart from each other with every passing second, the same way dots painted on a balloon spread apart as you blow air into it. This expansion was first confirmed nearly a century ago and has been measured, remeasured, and confirmed countless times since. The speed of that expansion has a name, the Hubble constant, named after astronomer Edwin Hubble. It tells scientists how fast galaxies are moving away from us for every unit of distance between us and them. Get that number right, and you unlock the ability to calculate the age of the universe, the size of the observable cosmos, and the distances to galaxies billions of light years away. For decades, measuring this number felt like a straightforward, if difficult, engineering problem. Point better telescopes at farther objects, refine your calculations, and the number should settle down to one agreed value. Scientists expected that as instruments improved, the uncertainty around the Hubble constant would shrink, the way a blurry photograph sharpens as you adjust the focus. That is not what happened. Instead, as measurements became more precise, two completely different methods for calculating the Hubble constant started disagreeing with each other more clearly, not less. One method looks at the oldest light in the universe, leftover radiation from just a few 100,000 years after the Big Bang. The other method looks at nearby stars and galaxies, using their brightness and distance to calculate how fast local space is stretching. Both methods are backed by decades of careful physics. Both have been checked, rechecked, and refined by different research teams working independently across different countries. And yet, they refuse to agree. The gap between them is not a tiny statistical fluctuation either. It sits at a confidence level scientists rarely dismiss as noise, a level where saying, "it's probably nothing," starts to feel intellectually dishonest. Imagine two separate teams of surveyors measuring the exact same mountain, one using satellite lasers, the other using old-fashioned ground instruments. If they came back with heights differing by a few inches, nobody would blink. But if one team measured the mountain at 10,000 feet and the other measured it at 11,000 feet, using techniques both considered reliable, everyone would demand an explanation. That is roughly the scale of disagreement scientists are facing with the Hubble constant, translated from mountains into the expansion rate of everything that exists. This mismatch became known as the Hubble tension, and it has grown into one of the most stubborn puzzles in modern cosmology. Not a niche curiosity discussed by a handful of specialists, a genuine crisis sitting at the center of how scientists understand the size, age, and structure of everything. Entire conferences are now built around this single disagreement. Some physicists have proposed exotic new forms of dark energy, changing over time in ways nobody predicted. Others have proposed subtle flaws in the physics of the early universe itself. None of these ideas have won broad, lasting acceptance. And once researchers started searching for explanations closer to home, instead of further out in exotic physics, one candidate kept resurfacing, quietly connected to everything we've covered so far. Our own empty neighborhood. To understand why the Hubble tension matters so much, picture two clocks hanging on the same wall, both supposedly showing the exact same time. One clock uses gears and springs, built from ancient, reliable technology. The other uses a modern quartz crystal, precise and modern, in a completely different way. If both clocks are accurate, they should show the same time, second for second. Instead, imagine they consistently disagree by several minutes every single day, no matter how many times you check the batteries or adjust the gears. That is essentially what is happening with the Hubble constant. The first clock uses the cosmic microwave background, the faint afterglow of the Big Bang, still detectable, filling every direction of the sky. By carefully analyzing tiny temperature variations in this ancient light, combined with well-tested physics of the early universe, scientists calculate an expansion rate of roughly 46,000 miles per hour for every million light-years of distance between 2 points in space. The second clock uses something called the cosmic distance ladder, a step-by-step chain of measurements starting with nearby stars whose distances we know precisely, moving outward to more distant stars, and finally to exploding stars called supernovae, bright enough to be seen across billions of light-years. This method produces a noticeably higher number for the expansion rate, roughly 10% faster than the cosmic microwave background method predicts. 10% might sound small. It is not. In cosmology, a 10% disagreement between two independently verified measurement techniques is enormous. The equivalent of two separate teams of engineers calculating the size of the same bridge and coming up with answers that differ by hundreds of feet. Something, somewhere, has to be wrong, or at least incomplete. For years, scientists assumed the mismatch would eventually vanish as instruments improved and calculations were refined. That has not happened. If anything, the disagreement has become more statistically significant over time, not less, as more data pours in from more telescopes, more supernovae, and more independent research teams. Every attempt to explain away the gap as simple measurement error has failed to fully resolve it. Teams have double-checked their calibrations, cross-referenced their instruments against each other, and repeated their observations using entirely separate telescopes built by separate space agencies. The gap survives every retest. That kind of stubborn persistence is exactly what convinces scientists a problem is real rather than a fluke, and it is exactly what pushed the Hubble tension from a minor footnote into a headline problem in physics. That failure forced physicists to consider stranger possibilities. Maybe the standard model of cosmology, the framework used to interpret the ancient light from the Big Bang, is missing something fundamental. Or maybe, just maybe, the problem is not a flaw in the theory of the entire universe. Maybe the problem is location. Maybe the nearby measurement, the one using stars and supernovae close to home, is being distorted by something specific to our exact position in space. That single shift in thinking, from the universe is broken to our neighborhood is unusual, changed the entire direction of the investigation. It meant the fix might not require rewriting the laws of physics at all. It might simply require admitting that the ground beneath our own telescopes is not the flat, average launch pad everyone assumed it to be. Here is the idea that turned a global measurement dispute into a local mystery. Both methods for measuring the Hubble constant assume, as a basic starting point, that our local region of the universe looks roughly typical. Average density, average distribution of galaxies. Nothing unusual about our specific address in the cosmos. Remove that assumption, and the entire calculation shifts. Remember the KBC void, stretching roughly 2 billion light-years across, with us sitting somewhere near its emptier core. If that void is real, and multiple independent surveys strongly suggest it is, then our local region is anything but typical. It is significantly emptier than a random patch of the universe has any right to be, and an underdense region does something specific and measurable to the galaxies inside it. Here's the mechanism, explained without the heavy math. Galaxies near the edge of a void feel a gravitational tug from the denser regions surrounding that void, the same way objects near the rim of a shallow bowl slowly slide toward its deeper edges. That tug creates outward motion on top of the universe's normal expansion. Picture a river already flowing downstream, and then imagine someone opens a floodgate nearby, adding extra current, pushing everything along even faster. If we are living inside a void experiencing this outward push, then when we measure how fast nearby galaxies are receding from us using supernovae and the cosmic distance ladder, we are measuring the universe's true expansion rate, plus a local boost caused by our void's gravitational outflow. It would be like clocking a car's speed while someone off-camera is also pushing it from behind. The speedometer reads real numbers, but those numbers no longer reflect the engine alone. That local boost could explain why the nearby measurement, using stars and supernovae, comes out roughly 10% faster than the measurement based on the ancient light from the early universe, which reflects an average taken across enormous cosmic distances, far beyond any single void's influence. Different scales, different results, because one of them is quietly contaminated by exactly where we happen to be standing, while the other averages across a volume too vast for any single void to skew. Researchers who first proposed this connection calculated that a void with roughly the size and depth of the one surrounding us could account for a meaningful chunk of the missing 10%, possibly even the majority of it, depending on exactly how deep the emptiness truly extends. That calculation turned a strange coincidence, an empty neighborhood sitting next to an unexplained measurement gap, into something scientists could actually test with numbers instead of speculation. This idea does not ask scientists to abandon known physics. It does not require exotic particles or bizarre new forces. It simply asks a humbling question. What if the reason the numbers do not match is a flaw in our assumption that our corner of the universe is nothing special? It is, in a strange way, a comforting explanation and an unsettling one at the same time. Comforting, because it does not demand new laws of physics nobody has ever seen. Unsettling, because it demands giving up the quiet assumption that our slice of the cosmos represents the whole. And once researchers began treating that question seriously, they needed to test it with something more rigorous than intuition. They needed simulations, models, and hard statistical tests to see if the idea could actually survive scrutiny. Testing whether a void can explain the Hubble tension is not something you can do with a telescope alone. You need a different kind of tool, a simulated universe, built entirely inside a supercomputer, following the same physical laws scientists believe govern the real cosmos. Researchers feed in initial conditions based on the early universe. Let gravity do its work across simulated billions of years, and watch how matter clumps into galaxies, filaments, and voids. One of the most important simulations used for this purpose is called the MXXL simulation, a massive computational model built to mimic how structure forms across the universe, according to the standard cosmological framework known as lambda cold dark matter, or lambda CDM for short. Think of it as running the universe's history millions of times over inside a machine, checking each time how likely certain outcomes are to occur. Researchers used this simulation to ask a very specific question. If you randomly picked billions of different starting points inside a simulated universe built exactly like lambda CDM predicts, how often would you land inside a void as large and as empty as the one we appear to occupy? The answer was striking. Scientists calculated that finding ourselves inside a void matching the KBC void's size and depth, purely as a random accident, would happen at a confidence level exceeding 6 standard deviations away from what's typical. To put that number in plain terms, 6 standard deviations describes an event so statistically unlikely that, in most fields of science, it would be treated as essentially impossible under the assumed model. Physicists sometimes call 5 standard deviations a discovery threshold, the point at which scientific results are considered confirmed rather than coincidental. This void's unlikeliness cleared that threshold and kept going. When researchers combined this statistical tension with the existing Hubble tension, the numbers stacked together into a confidence level exceeding 7 standard deviations against the standard cosmological model. That is not a subtle anomaly buried deep in the noise of imperfect data. That is a number that makes cosmologists sit up straight in their chairs. For comparison, the discovery of the Higgs boson, one of the most celebrated confirmations in modern physics, was announced once evidence crossed the 5 standard deviation threshold. 7 standard deviations sits well beyond that historic bar. Researchers do not throw around numbers like this casually, and seeing one attached to something as mundane sounding as where we happen to live caught the attention of the entire field. This does not mean the entire framework of modern cosmology is broken beyond repair. Science rarely works through single dramatic collapses, but it does mean that the standard model, as currently built, struggles badly to explain both the size of the void we live in and the size of the Hubble tension at the same time, using only random chance as the explanation. Picture buying a single lottery ticket and winning the jackpot on your very first try. Possible, sure, but if it happens to 5 different people in your family on their very first tickets, you would stop calling it luck and start looking for a rigged machine? That is roughly the position cosmologists found themselves in, staring at a void, this improbable sitting, exactly where we happen to live. Something appears to be missing from the picture, and researchers began asking whether the fix required rethinking the underlying rules of gravity itself, reaching well beyond our own local neighborhood. For nearly a century, scientists have relied on lambda cold dark matter to describe how the universe evolved from the hot, dense aftermath of the Big Bang into the vast web of galaxies we see today. This model has passed test after test, matching observations of the cosmic microwave background, the large-scale distribution of galaxies, and the abundance of light elements formed in the universe's first few minutes. It is not a model built on guesswork. It is built on decades of successful predictions. But successful models can still contain cracks, especially at the largest and smallest scales, the places where theories get pushed to their limits. The KBC void, combined with the Hubble tension, represents exactly this kind of stress test. When researchers calculated how unlikely it would be, under standard theory, to randomly find ourselves inside a void this large and this empty, and then combine that with the existing tension in expansion rate measurements, the resulting statistical pressure on the standard model became difficult to dismiss casually. This is where trust and honesty in science matter most. A confirmed void exists. Confirmed measurements show a real gap between different methods of calculating cosmic expansion. What remains genuinely uncertain, actively debated among specialists, is exactly how these two confirmed facts connect, and whether explaining both requires only a rare cosmic accident or something deeper about the laws of gravity itself. Some researchers have proposed that instead of tweaking the standard model with small adjustments, scientists should consider alternative theories of gravity entirely. One such idea, called modified Newtonian dynamics, or MOND, changes how gravity behaves at extremely large scales and extremely weak strengths, the kind found in the thin, empty stretches of a cosmic void. Under this alternative framework, some scientists argue that voids as large and as deep as the one we live in become far less statistically surprising, forming naturally rather than requiring an improbable roll of cosmic dice. This remains one of the most contested corners of modern astrophysics. MOND has passionate supporters and equally passionate critics, and it has not replaced the standard model in mainstream cosmology. Most scientists still consider lambda CDM the best supported framework overall, especially given its success, explaining the cosmic microwave background in exquisite detail. But the fact that alternative gravity models can address the void's improbability at all shows just how seriously some researchers are taking this challenge. Critics of MOND point out that it struggles to explain other well-tested phenomena, particularly the behavior of galaxy clusters and the fine details of the cosmic microwave background, areas where lambda CDM performs remarkably well. The debate is not close to settled, and most working cosmologists remain cautious about abandoning a framework with such a long track record of success over one still working to prove itself at every scale. None of this settles the debate. If anything, it deepens it, turning a simple regional oddity, an empty patch of space near our galaxy, into a genuine pressure point, testing the foundations of modern cosmology. Whichever framework eventually wins out, standard theory patched with new explanations or a fundamentally different picture of gravity, the void we live inside has become impossible for cosmologists to simply wave away as a coincidence. And as we're about to see, not every scientist agrees the void deserves this much credit. Some researchers argue the entire connection between our local emptiness and the Hubble tension has been overstated from the very beginning. Science does not move forward through unanimous agreement. It moves forward through disagreement, tested against evidence, until only the strongest explanations survive. The idea that our local void explains the Hubble tension has real supporters among respected researchers, but it also has serious critics, and their objections deserve just as much attention as the original idea itself. One major objection involves distance. The Hubble tension shows up in measurements taken from much farther away too, sources whose light traveled for a significant fraction of the universe's entire history before reaching our telescopes, well beyond the relatively nearby supernovae, close enough to potentially feel the void's outward push. If the void's gravitational outflow only affects our immediate neighborhood, roughly the first billion light-years surrounding us, critics argue it should not meaningfully influence measurements taken from sources far beyond that boundary. Yet the tension persists, even in those more distant measurements, weakening the case that our local emptiness is the sole culprit. Other researchers have directly tested the void hypothesis using different types of distance measurements entirely, moving beyond supernovae toward other reliable cosmic yardsticks, including a method called baryon acoustic oscillations, essentially frozen ripples left over from the early universe that act as a natural ruler for measuring cosmic distances. Some of these independent tests have failed to find the exact signature you would expect if a void alone fully explained the Hubble tension, suggesting the void might account for only part of the discrepancy, not the entire gap. Nobody seriously argues the KBC void doesn't exist, and nobody dismisses the void itself. Multiple independent surveys, using different telescopes and different wavelengths, confirm the deficit of galaxies surrounding us. The disagreement is narrower and more precise. Does this confirmed emptiness fully explain the confirmed tension in expansion measurements? Or does it only explain a fraction of it, leaving the rest of the mystery still unsolved? Some researchers have proposed a middle position. Perhaps the void contributes meaningfully to the Hubble tension, easing part of the disagreement between measurement methods, while some additional unknown factor, still undiscovered, accounts for the remaining gap. Under this view, our cosmic neighborhood matters, but only partially. It is one confirmed puzzle piece inside a larger, still incomplete picture. This split among experts is worth sitting with for a moment. It is not a fringe idea being dismissed by the mainstream, and it is not an accepted fact taught in every classroom either. It sits in the genuinely uncertain middle ground of active research, the space where real scientific progress actually happens, argued out year by year through new data rather than settled by a single dramatic announcement. This kind of careful, contested debate is exactly how real science operates, messier and more honest than a tidy, simple explanation. It is tempting to want a clean, single answer, one villain, one hero, one confirmed cause. Real cosmology rarely offers that comfort. It offers competing evidence, careful teams checking each other's work, and slow, hard-won progress towards something closer to the truth. It means the story of our cosmic whole is far from finished. To move forward, scientists needed more than debate. They needed sharper tools, wider surveys, and fresh data capable of testing the void's true size, shape, and influence with far greater precision than ever before. If scientists want to settle this debate, they need one thing above all else: better maps, detailed, three-dimensional charts, plotting the precise position of millions of galaxies across billions of light-years, sharp enough to trace the exact boundaries of the void we appear to be living inside, well beyond the rough estimates built from a handful of earlier galaxy surveys. This is exactly the kind of project modern astronomy has been racing to complete. Wide-field surveys, using instruments capable of photographing enormous stretches of sky in a single pass, are gathering galaxy positions at a scale earlier astronomers could only dream about. Where Kirshner's original Boetes void discovery relied on plotting a few thousand galaxies by hand-guided observation, modern surveys can catalogue millions of galaxies across vast regions, building maps precise enough to trace subtle changes in density from one region of space to the next. These newer surveys allow scientists to test the void hypothesis with far sharper tools than simple galaxy counting. Instead of just asking how many galaxies exist in a given patch of sky, researchers can now measure the actual motion of galaxies, tracking their velocities directly, checking whether they move in the specific outward pattern you would expect if they were being pushed by a void's gravitational imbalance, rather than simply drifting with the universe's overall expansion. One especially useful method compares galaxy distances, measured two completely different ways. Once, using a technique called the Tully-Fisher relation, which estimates distance based on how fast a galaxy spins, and once using redshift, which estimates distance based on how much a galaxy's light has stretched due to cosmic expansion. If a void's outflow is real, these two measurements should show a specific, predictable mismatch for galaxies located near the void's edges, a signature distinct from ordinary cosmic expansion alone. Early results from these more detailed tests have offered support for the void's existence and its underdense nature, while still leaving its precise depth and exact influence on the Hubble tension only partially resolved. Science rarely delivers instant, complete answers. It delivers incremental progress, each new survey sharpening the picture slightly more than the last, narrowing uncertainty rather than eliminating it outright. Some of this newer work has focused specifically on galaxies right at the void's presumed boundary, the transition zone between our empty neighborhood and the denser walls surrounding it. Measuring exactly how those boundary galaxies move offers one of the cleanest possible tests, since their motion should show the clearest fingerprint of an outward gravitational push if the void hypothesis is correct. What makes this moment particularly exciting is timing. Several major astronomical surveys, built specifically to map cosmic structure with unprecedented precision, are actively collecting data right now, with results expected to refine our understanding of the void's true shape and strength in the coming years. For the first time in this decades-long story, scientists are actively mapping our cosmic neighborhood rather than simply theorizing about it, piece by piece, with tools sharp enough to settle century-old assumptions about our place in the universe. None of these tools existed when Brent Tully first noticed a strange gap near the local group, or when Kirshner's team stumbled onto the emptiness of Boetes. Each generation of astronomers has handed the next generation sharper eyes, and the current generation is pointing those eyes directly at the ground beneath our own feet, cosmically speaking, determined to finally settle exactly how empty our neighborhood really is. Step back from the technical details for a moment and consider the bigger picture this discovery paints. If the KBC void is real, and current evidence strongly suggests it is, then our cosmic address is not average. It is not typical. It is not the safe, unremarkable location many scientists assumed for most of the 20th century. We appear to be living in a genuine outlier, a rare pocket of emptiness inside an otherwise densely structured universe. This matters far beyond simple curiosity about our neighborhood. It touches something closer to identity, the quiet story every generation of scientists has told about our place in the grand structure of everything. Modern astronomy relies heavily on an assumption called the cosmological principle, the idea that on large enough scales, the universe looks roughly the same in every direction, from every vantage point. This principle underlies countless calculations, from estimating the universe's age to predicting how galaxies should cluster across cosmic time. A void as large and as deep as the one we appear to occupy does not necessarily break the cosmological principle entirely. On truly enormous scales, spanning many billions of light years, the universe likely still averages out to something roughly uniform. But it does mean that on the specific scale relevant to our local measurements, the scale used to calculate the Hubble constant using nearby supernovae, our neighborhood behaves nothing like a typical, average sample of the cosmos. Think about what this means for scientific measurement in general. Imagine trying to calculate the average height of every person on Earth, but your only sample comes from a single professional basketball team. Every individual measurement would be accurate and honestly recorded, yet the final average would be badly skewed, simply because the sample itself was never representative of the whole population. If our local universe is similarly unrepresentative, unusually empty compared to the cosmic average, any measurement relying on nearby galaxies alone risks carrying a hidden, structural bias. This reframes the entire Hubble tension conversation. It stops being simply a disagreement between two clever measurement techniques and becomes a deeper question about whether our specific vantage point in the universe can ever give us a truly unbiased view of the whole. Every telescope we build, every galaxy we measure, every calculation of cosmic distance starts from exactly where we are standing, deep inside an underdense bubble that may not represent the wider universe at all. It is worth pausing on how quietly this shift happened. Nobody set out expecting basic geography to matter this much. The Hubble tension was first treated as a pure measurement puzzle, something to be solved with better telescopes and cleaner math. Only gradually did scientists realize the puzzle might be tangled up with something as simple and as strange as which specific patch of an almost infinite universe we happen to call home. That question applies well beyond the Hubble constant. It potentially applies to any measurement built on the assumption that our local slice of the cosmos looks like everywhere else. Every textbook diagram of the universe's shape, every estimate of how galaxies typically cluster, every model calibrated using our own cosmic backyard as a stand-in for the average carries at least a small risk of inheriting this same quiet distortion. And that uncomfortable possibility pushes this story past a single astronomical puzzle into something closer to a fundamental challenge about how confidently we can ever claim to understand the universe beyond our own cosmic backyard. Once scientists accepted that our neighborhood might be unusually empty, a much larger question followed naturally. If living inside a void can distort measurements of cosmic expansion, what else might it be quietly distorting? The Hubble constant is not an isolated number sitting off to the side of astronomy. It threads through nearly every major calculation cosmologists perform. Consider the age of the universe. Scientists calculate this age, partly using the expansion rate, running the cosmic clock backward from today's measurements, to estimate when everything began expanding from an extremely hot, dense state. If the local measurement of that expansion rate carries a hidden bias caused by our void's outward push, then calculations relying heavily on nearby measurements could shift the estimated age of the universe by a small but meaningful amount, compared to calculations based purely on the ancient cosmic microwave background. Consider also the size of the observable universe itself. Distances to faraway galaxies are calculated using a careful chain of measurements, each step calibrated against the ones before it, all the way back to nearby reference points relatively close to Earth. If that starting point, our own local neighborhood, behaves differently than a typical region of space, then every distance calculated further up that chain inherits a small piece of that original distortion, like a tiny error at the base of a tall ladder becoming amplified with every additional rung. This does not mean cosmologists have been getting everything wrong, and it does not mean decades of careful work should be thrown out. Most large-scale conclusions about the universe rest on multiple independent lines of evidence, not a single measurement chain. The cosmic microwave background, unaffected by any local void because it comes from light that traveled across the vast majority of the universe's history, still provides a powerful, largely bias-free check on many of these calculations. Scientists are not lost. They are, however, forced to be more careful about assumptions built on our local surroundings. This kind of careful re-examination is not a weakness in science. It is exactly how science is supposed to work. A field confident enough to question its own assumptions, willing to test whether long-held beliefs about our typical, average cosmic address actually hold up under new evidence, is a field functioning exactly as intended. The void does not prove modern cosmology is broken. It proves modern cosmology is still actively being tested, refined, and improved, even in areas many assumed were settled decades ago. Think of it less like discovering a crack in a building's foundation, and more like discovering that the surveyor who measured the land generations ago was standing on slightly uneven ground. The building itself may still be sound, but every measurement taken from that original uneven spot deserves a second look, just to be sure nothing subtle slipped through unnoticed. This same tension, careful confidence, balanced against honest uncertainty, shows up throughout the history of astronomy. Every generation believes it has finally mapped reality correctly, only for the next generation, armed with sharper instruments, to discover a subtle distortion nobody could have detected before. There is no shame in that pattern. It is simply how understanding the universe actually works, one corrected assumption at a time. And that leads to the final, most unsettling layer of this story. Because if our specific position inside the universe can distort measurements this significantly, it raises a much older philosophical question, one astronomers have wrestled with for centuries, now returning with new, sharper evidence behind it. For centuries, one guiding assumption has anchored nearly all of astronomy. We are not special. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. This principle, sometimes called the Copernican principle after the astronomer who first dethroned Earth from the center of everything, has guided scientific thinking for hundreds of years, and it has been right, again and again, every time it has been tested. The KBC void does not overturn that principle entirely. Nobody is claiming Earth sits at some sacred cosmic center point, but it does introduce a subtler, more uncomfortable twist. Being unremarkable in position does not guarantee being unremarkable in surroundings. We can be one ordinary galaxy among countless others, following the same physical laws as everywhere else, while still happening to sit inside a rare, statistically unusual pocket of empty space. Both things can be true simultaneously. Nothing special about us, yet something unusual about exactly where we ended up. This distinction matters enormously for how we interpret everything we observe. Every measurement, every calculation, every conclusion about the universe's age, size, and expansion rate starts from the same fixed vantage point, right here, inside this specific region of space. If that region turns out to be meaningfully unrepresentative of the wider cosmos, then some of our most confident conclusions about the universe as a whole may carry a subtle, local fingerprint baked in from the very beginning, difficult to fully remove no matter how carefully scientists calculate. Consider an analogy. Imagine studying ocean currents entirely from data collected inside a single, unusually calm harbor, sheltered from the open sea by a natural rock formation. Every measurement taken inside that harbor would be completely accurate, honestly recorded, real data. Yet using those measurements alone to describe the behavior of the entire ocean would produce a badly skewed picture, simply because the harbor is not representative of open water. Astronomers are now grappling with the possibility that our entire galaxy sits inside a similar kind of sheltered harbor, a vast, underdense bubble stretching roughly 2 billion light-years across, quietly shaping some of the very measurements we use to understand the universe beyond it. This does not mean our picture of the cosmos is fundamentally wrong. Multiple independent lines of evidence, including the ancient light of the cosmic microwave background, remain untouched by our local void, offering a crucial outside check on everything else. That check matters more than it might seem. It means humanity is not sailing blind, relying solely on measurements taken from inside a potentially misleading harbor. We have at least one instrument, the leftover light from the Big Bang itself, that samples the ocean far beyond our sheltered corner, giving scientists a genuine anchor point to compare against everything measured closer to home. But it does mean the story of the universe, as told from planet Earth, may carry a quiet, built-in distortion, one scientists are only beginning to fully measure and correct for. And that distortion connects directly to a question growing more urgent with every new survey. Exactly how large is this hole? Exactly how deep does it go? And exactly how much of what we think we know about reality has been shaped by simply standing in the wrong place to see it clearly? To understand why a void near us matters so much, you have to see the full shape of the universe first. The shape scientists spent decades piecing together from millions of individual measurements. Once you see it, you cannot unsee it. The universe is not a random scatter of galaxies, like sand thrown across a table. It is something closer to a giant, glowing net, stretched across billions of light-years, with galaxies clumped along its threads and almost nothing filling the gaps between them. Astronomers call this structure the cosmic web. Picture a spider's web the size of everything, its threads made not of silk but of galaxies, gas, and invisible dark matter, all pulled together by gravity over billions of years. Where threads cross, you find dense knots containing thousands of galaxies packed together, called nodes. Along the threads themselves, you find long filaments of galaxies stretched like strings of lights, and in the wide open spaces between those threads, you find voids. Vast, nearly empty canyons carved out of the universe. The scale of this pattern is almost impossible to picture using ordinary comparisons. A typical void stretches somewhere between 100 million and 500 million light-years across. If you shrank the entire observable universe down to the size of a basketball, a single void would still be larger than a grain of sand resting on its surface. And there are thousands upon thousands of them scattered throughout that ball. Here's a detail that reshapes how you think about empty space itself. Voids are not evenly distributed leftovers, random gaps left behind by chance. They make up close to 80% of the universe's total volume, while holding only around 20% of its mass. In other words, most of the universe, by sheer three-dimensional space, is void. Galaxies, stars, planets, and everything you have ever seen with your own eyes cling to the thin walls and threads surrounding these enormous empty regions. Like moss growing along the cracks of an otherwise bare stone, This changes the entire framing of our earlier discovery. The KBC void is not some freakish, one-of-a-kind wound in an otherwise smooth universe. It is one entry in a vast catalogue of similar structures, an ordinary feature of cosmic architecture, just unusually large and unusually close to home. What makes our situation different is not that voids exist, it is that we happen to live inside one large enough and near enough to actually distort measurements taken from Earth. And once scientists understood the true scale and role of voids across the universe, an even stranger idea started gaining traction. What if these empty canyons are not simply passive gaps left behind by galaxy formation? What if they are actively doing something, quietly shaping one of the greatest mysteries in modern physics? The unexplained force scientists call dark energy. This idea did not emerge overnight. It grew slowly, as astronomers gradually realized that voids were not simply the leftover negative space of galaxy surveys, unremarkable regions worth ignoring in favor of the bright, crowded structures nearby. And once astronomers started treating voids as active participants in cosmic history rather than passive gaps, an entirely new chapter of cosmology opened up, one that connects directly back to the strange emptiness surrounding our own galaxy. Here's a fact that stops most people cold the first time they hear it clearly explained. The universe is expanding faster and faster, accelerating outward like a car pressing harder on the gas pedal rather than coasting at a steady speed. Scientists discovered this acceleration in the late 1990s, and it completely upended what astronomers had expected. Gravity should be slowing expansion down over time, not speeding it up. To explain the acceleration, physicists proposed something called dark energy, an invisible force or property of space itself that pushes everything apart. Nobody fully understands what dark energy actually is. It has never been directly detected in a laboratory. Its existence is inferred entirely from its effects, the way you might infer wind exists by watching leaves scatter across a yard without ever seeing the air itself. Despite that mystery, dark energy is not a fringe idea. It is baked into the standard model of cosmology, accounting for roughly 70% of everything in the universe, more than matter and dark matter combined. Here on Earth, dark energy is completely undetectable in daily life. Matter is packed so densely around us that ordinary gravity overwhelms any trace of the outward push entirely. Throw a baseball, and it follows exactly the arc physics has always predicted. Dark energy plays no detectable role in any of it. Its influence only becomes significant across enormous, largely empty stretches of space, far beyond anything a human being could ever directly experience. Here is where voids re-enter the story in a completely new way. Scientists have discovered that dark energy's influence is not spread evenly across the cosmos. Inside dense regions, galaxies, clusters, filaments packed tightly with matter, gravity from all that surrounding mass overwhelms dark energy's gentle outward push. Matter wins. Structures hold together. But inside voids, where matter has thinned out to a fraction of the average, there is almost nothing left to counteract dark energy's push. Here, the invisible force runs essentially unopposed. This means voids are not simply empty, they are active. Scientists have found that voids expand measurably faster than the rest of the universe's overall average expansion rate, growing wider and emptier as billions of years pass, stretched more aggressively by dark energy precisely because there is so little matter inside them to resist it. Picture a nearly empty balloon and a tightly packed balloon both being inflated by the same machine. The empty one stretches faster, its thin, sparse walls offering less resistance to the air rushing in. Some researchers have taken this idea even further, proposing something genuinely radical. What if dark energy is not a separate, mysterious ingredient added to the universe at all? What if the accelerated expansion scientists observe is simply what happens naturally when huge, nearly empty voids grow faster than dense regions? creating the illusion of a universal acceleration without requiring any exotic new physics whatsoever. Under this view, the voids themselves, canyons of nothing stretched between galaxies, might be quietly generating one of the greatest unsolved mysteries in modern science, simply by existing and expanding the way empty things naturally do. This remains a minority position among cosmologists, tested against mainstream dark energy models and still facing significant challenges of its own. But the fact that serious researchers take it seriously at all reveals something important about how central voids have become to modern cosmology, treated by leading researchers as a genuine window into the deepest unanswered question in physics: what dark energy actually is and why it exists at all. Long before scientists connected voids to dark energy, another mystery was already waiting in the oldest light in the universe: the cosmic microwave background, the faint afterglow of the Big Bang stretched across the entire sky. This ancient light should look almost perfectly uniform in every direction, varying only by the tiniest fractions of a degree from one patch of sky to the next. And for the most part, it does, except for one place. In 2004, scientists studying detailed maps of this ancient radiation noticed something strange in the direction of the constellation Eridanus, a patch of sky noticeably colder than everywhere around it, standing out from the smooth, predictable pattern like an unexpected shadow. They called it the cold spot, and it immediately became one of the most argued about anomalies in modern cosmology. Why would a patch of ancient light be colder than its surroundings? One elegant explanation involves voids. As light from the Big Bang travels toward Earth across billions of years, it sometimes passes through enormous underdense regions along the way. Passing through a void, the light briefly gains a small amount of energy entering the empty region. But if that void is actively growing and stretching wider as dark energy expands it, the light loses slightly more energy, leaving than it gained entering. The net result is a tiny, measurable cooling, a signature suggesting the light crossed something unusually empty on its way to us. This effect carries a technical name, the integrated Sachs-Wolf effect, though the mechanism behind it is simpler than the name suggests. Think of a ball rolling down into a shallow depression, then climbing back out the other side. If the depression stayed perfectly still, the ball would exit with exactly the energy it entered with. But if the depression is slowly flattening out while the ball crosses it, stretched wider by some outside force, the ball exits with slightly less energy than it started with. Light crossing a growing void behaves the same way, arriving at our telescopes very slightly cooler than it otherwise would. Excited researchers searched the region of sky, matching the cold spot, and found exactly what they hoped for: an enormous supervoid sitting directly along that line of sight, one of the largest structures ever detected, stretching hundreds of millions of light years across. For years, this felt like a clean, satisfying explanation, but newer, more careful surveys have complicated that tidy story considerably. Some researchers, using deeper galaxy surveys and gravitational lensing measurements, have argued the supervoid in that direction is not actually large enough or deep enough to fully explain the cold spot's chill using standard physics. Measurements of how strongly the void bends the light of galaxies behind it suggest its true mass is weaker than its apparent emptiness implies, deepening the puzzle rather than resolving it. That leaves two uncomfortable possibilities on the table. Either the cold spot is simply an extreme, unlikely statistical fluctuation, unrelated to any void at all, or the physics connecting voids to this cooling effect is stronger than the standard model currently predicts, hinting that dark energy behaves in voids in ways not yet fully understood. Neither option is comfortable for cosmologists. The debate remains active and unresolved, argued out paper by paper as new data arrives. But notice the pattern quietly repeating itself now for the third time in this story. Once again, an unexplained cosmic anomaly. Once again, a suspiciously placed void nearby. and, once again, real uncertainty about whether the connection is meaningful physics or simple coincidence. By this point in the story, a pattern has emerged that deserves a moment of honest reflection. The Hubble tension, sitting suspiciously close to our own giant void, the cold spot, sitting suspiciously close to another giant void, hundreds of millions of light years away, in a completely different direction. Dark energy itself, behaving in ways that seem to concentrate specifically inside empty regions rather than spreading evenly across the cosmos. Three separate mysteries, three separate hints pointing toward the same suspect: enormous, nearly empty voids, quietly shaping measurements far beyond their own borders. Scientists have a healthy, built-in skepticism toward patterns like this. Coincidences happen constantly across a universe this vast, and human brains are notoriously good at spotting patterns that are not really there, connecting unrelated dots into a story that feels satisfying but is not actually supported by hard evidence. Extraordinary claims require extraordinary evidence, and voids explain everything strange we've found would count as an extraordinary claim. And yet, dismissing the pattern entirely would ignore something equally important. Each individual thread in this story rests on real, independently confirmed observations, not speculation. The KBC void's existence is confirmed across multiple wavelengths of light. The Hubble tension is confirmed by multiple independent measurement teams. The accelerated expansion of voids under dark energy is grounded in decades of established cosmological theory, not a fringe guess. The cold spot itself is a real, measured anomaly in Planck satellite data, not a rumor. None of these threads are invented. What remains genuinely uncertain is only how tightly they connect to each other. This is precisely the uncomfortable, unresolved middle ground where real frontier science lives. Not proven fact, not baseless speculation, a genuine open question, actively being tested with better telescopes, sharper statistics, and larger surveys every single year. Scientists studying this area describe themselves as neither confident the voids explain everything, nor confident they explain nothing. They describe themselves as still gathering evidence. There is a useful analogy here, borrowed from criminal investigation rather than physics. A detective who finds the same suspect's fingerprints at three separate, unconnected crime scenes does not immediately declare the case solved. But the detective also does not dismiss the pattern as meaningless coincidence and walk away. The responsible move is to keep investigating, gathering more evidence, testing the connection rigorously before reaching a final conclusion either way. That is exactly the posture serious cosmologists have adopted toward the growing pile of void-related anomalies stacking up across completely different corners of astrophysics. What makes this particular open question so compelling is the stakes attached to it. If it eventually turns out that voids like ours meaningfully distort multiple major cosmological measurements at once, the consequences would reach far beyond resolving a couple of stubborn anomalies. It would force a genuine reckoning with how confidently humanity can claim to understand the shape, age, and fate of the entire universe, using data gathered from inside one of its rarest, emptiest neighborhoods. And that reckoning connects directly to a question even bigger than measurement bias. What happens to a universe increasingly dominated by empty, accelerating voids over the unimaginably long stretches of time still ahead? That question pulls this story away from careful statistics and measurement debates and towards something closer to prophecy, a look forward across timescales that dwarf anything covered so far. The same emptiness responsible for our local measurement puzzles is, according to current theory, actively growing wider with every passing billion years, quietly rewriting the architecture of the entire cosmos far beyond anything visible from Earth today. Voids are not static. They are not simply holes carved out once, then left frozen in place for the rest of cosmic history. They grow, slowly, relentlessly, over billions upon billions of years, driven by the same dark energy quietly reshaping everything else in this story. Voids expand wider and empty out further, pressing outward against the walls and filaments surrounding them. Here is what that growth means for the long-term future of the cosmic web itself. As voids swell, the dense structures separating them, the filaments and walls where galaxies live, get squeezed and stretched thinner over time. Picture a sponge slowly losing its structure, its solid walls thinning as the holes inside it grow larger and larger, until eventually the whole thing barely holds together at all. Over spans of time measured in tens of billions of years, cosmologists expect this exact process to gradually unravel the elegant web of filaments and clusters that currently defines the large-scale structure of the universe. This slow unraveling is not a sudden catastrophe arriving on any single dramatic date. It is a gradual drift, imperceptible across a single human lifetime, imperceptible even across the entire history of human civilization so far, only becoming obvious when you compress billions of years of cosmic evolution into a single timeline and watch the voids visibly swallow more and more of the space once occupied by dense, connected structure. This does not mean galaxies themselves are in any danger. Individual galaxies, held together tightly by their own gravity, remain stable structures, unaffected directly by the accelerated expansion happening in the vast empty spaces around them. Your own galaxy, the Milky Way, will remain intact for the indefinite future, its stars continuing to orbit, its structure holding firm against the emptiness growing all around it. What changes is the connection between galaxies, not the galaxies themselves. As voids widen, the distances separating galaxy clusters stretch further and further, accelerated by dark energy's outward push. Eventually, over spans of time almost too large to comprehend, distant galaxy clusters, currently visible from Earth, will recede so far and so fast that their light will simply never be able to reach us again, vanishing from our observable universe entirely through pure, relentless separation rather than any kind of destruction. This transforms the story of our local void from a measurement puzzle into something closer to a preview. The KBC void surrounding us is not an isolated oddity destined to remain fixed and unchanging forever. It is an active, growing example of exactly the process expected to reshape the entire universe over the deep future, empty regions swelling wider, dense regions stretching thinner, dark energy quietly winning a slow, billion-year tug-of-war against gravity itself. Standing inside a void, then, offers a front-row seat to the same fundamental process, expected to eventually reshape the entire observable universe, compressed here into a scale close enough for scientists to study directly, using telescopes pointed at our own cosmic backyard rather than distant, unreachable corners of space and time. There is something almost humbling in that realization. The same emptiness that complicates our attempts to measure the Hubble constant accurately is, according to current models, a preview trailer for the eventual fate of everything, playing out early and close enough for us to study it directly, rather than waiting billions of years to watch it unfold everywhere else. Here's a thought experiment worth sitting with. What if, instead of forming inside a nearly empty void, our galaxy had formed somewhere else entirely, deep inside one of the cosmic web's dense filaments, surrounded by thousands of neighboring galaxies, rather than a comparative handful? How different would our entire understanding of the universe look today, simply because of where we happen to end up? Picture two versions of Earth, identical in every way except cosmic address. One sits inside our actual, unusually empty void. The other sits deep inside a crowded filament, surrounded by galaxy after galaxy stretching in every direction. Both versions of Earth develop telescopes. Both versions of Earth build careful, honest scientific institutions. Yet both versions, simply because of where they happen to be standing, would almost certainly calculate at least slightly different values for something as fundamental as the age and expansion rate of the entire universe. Astronomers who study this question point to something important. A denser cosmic neighborhood would fundamentally change what an observer on Earth could see and measure. More nearby galaxies would mean more nearby supernovae available for calculating cosmic distances, potentially producing a more accurate reading of the Hubble constant, one less likely to carry the local bias currently suspected of skewing our own measurements. The entire Hubble tension crisis, dominating headlines and conference talks for over a decade, might simply never have become the puzzle it is today. But a denser neighborhood would introduce its own complications too. More nearby galaxies would mean more gravitational interference, cluttering observations of the distant universe, more foreground light polluting attempts to study fainter, more ancient objects. Astronomers living inside a crowded filament might have found certain measurements easier, while other measurements became significantly harder, trading one set of challenges for a completely different set. This thought experiment reveals something important about scientific measurement in general, something easy to overlook when you are the one doing the measuring. Every observer, anywhere in the universe, watches the cosmos from one single fixed vantage point, unable to relocate to check their results from somewhere else entirely. A civilization forming inside a dense cluster would face its own unique blind spots, just as we face ours, forming as we did inside one of the emptiest regions cosmologists have ever mapped. There is no perfectly neutral vantage point anywhere in an infinite, structured universe. Every location carries its own particular advantages and its own particular distortions, baked into the geometry of wherever a civilization happens to arise. Recognizing this does not mean giving up on the goal of understanding the true universe accurately. It means understanding that reaching that goal requires actively identifying and correcting for exactly this kind of local bias, rather than assuming, by default, that wherever you happen to stand represents everywhere else equally well. This is, in many ways, the same lesson every field of careful observation eventually learns. A doctor studying disease only from patients in one specific city risks drawing conclusions that do not hold up nationally. A biologist studying a single, isolated ecosystem risks assuming its patterns apply everywhere on Earth. Cosmology now faces its own version of this exact challenge, forced to reckon with the fact that its entire dataset, every galaxy, every supernova, every measurement ever taken, originates from observers confined to one single, specific, unusually empty corner of an almost unimaginably large cosmos. Given everything we've covered, a reasonable person might start to wonder whether humanity can trust any of its measurements of the universe at all, if our own cosmic neighborhood turns out to be this unusual. Fortunately, cosmology is not entirely dependent on measurements taken from inside our local bubble. One extraordinary tool exists specifically capable of reaching past our void's influence entirely, offering a genuine outside check on everything else. That tool is the cosmic microwave background itself, the same ancient light responsible for revealing the cold spot several chapters ago. This light was released roughly 380,000 years after the Big Bang, when the universe first became transparent enough for light to travel freely across space. Crucially, that light has been traveling toward us for over 13 billion years, crossing an overwhelming majority of the observable universe's entire history and volume along the way. Compare that journey to the relatively short hop made by light from a nearby supernova, traveling perhaps a few 100 million light-years before reaching our telescopes. The cosmic microwave background's journey dwarfs that distance by a staggering margin, sampling conditions across a volume of space so enormous that it would take thousands of structures the size of our own local void, lined up end to end, just to match the total distance that ancient light has traveled to reach us. Here's why that matters so much for our story. Our local void, as enormous as it feels to us, stretches roughly 2 billion light-years across at most. The cosmic microwave background's journey toward Earth spans distances vastly larger than that, sampling an average taken across a volume of space so enormous that any single local void, no matter how large it feels from the inside, becomes a comparatively tiny wrinkle averaged out across the total journey. It is a little like judging the average depth of an entire ocean, rather than judging it using only the water sitting inside one specific, unusually shallow tide pool near the shore. This is precisely why cosmologists still trust the cosmic microwave background's measurement of the Hubble constant as a genuinely reliable anchor point, even while suspecting our local, nearby measurements might carry a hidden bias from the void surrounding us. The ancient light provides an outside perspective, immune to whatever distortions our own specific neighborhood might introduce into calculations based purely on nearby stars and galaxies. This detail transforms the entire Hubble tension mystery from a frightening crisis into something closer to a fascinating diagnostic tool. The disagreement between the two measurement methods is not necessarily evidence that either method is broken. It may instead be evidence that comparing a local measurement against a truly universal one reveals exactly the kind of local distortion scientists would expect to find if they happen to be observing from inside an unusually empty region of space. In other words, the mismatch itself might be the fingerprint proving we live somewhere unusual, rather than a sign that our tools have failed us. Framed this way, the entire Hubble tension stops looking like a crisis threatening to topple modern cosmology, and starts looking more like a uniquely valuable clue, one of the clearest pieces of evidence available anywhere for actually locating and measuring the boundaries of our own strange cosmic neighborhood, using nothing but the careful comparison of two trustworthy, independently verified rulers. If our own cosmic neighborhood is unusually empty, an obvious question follows almost immediately. Where exactly are the galaxies that should be here, according to standard cosmological predictions, but appear to be missing entirely? Are they simply absent, victims of some unusual quirk in how matter clumped together in this particular corner of space billions of years ago? Or are some of them hiding somewhere astronomers have not yet managed to look carefully enough? This question sent researchers hunting through some of the most difficult regions of sky to study, particularly a strip of sky astronomers call the zone of avoidance, the section blocked from clear view by the thick dust and crowded stars of our own galaxy's disk. Roughly 1/5 of the entire sky sits partially hidden behind this dusty curtain, making it genuinely possible that some galaxies within our void's boundary have simply escaped detection, obscured rather than absent. Searching this hidden strip requires patience most casual observers never see. Astronomers pore over faint infrared signals, tiny blips of radio emission, and careful photographic comparisons stretching back decades, looking for the unmistakable signature of a small, dim galaxy hiding directly behind the glare and dust of our own Milky Way. It is painstaking work, more like sifting through sand for tiny fragments than the dramatic image most people picture when they imagine astronomical discovery. Using infrared telescopes capable of seeing through dust that blocks ordinary visible light, along with radio surveys tuned to detect the signature glow of hydrogen gas inside distant galaxies, astronomers have painstakingly searched this hidden strip for missing structures. They have found a handful of previously unknown dwarf galaxies scattered within our local void's boundaries, faint, gas-rich objects easily overlooked by earlier, less sensitive surveys. But here's the critical detail. Even after years of careful searching, these newly discovered dwarf galaxies remain far too few and far too small to meaningfully close the enormous gap between what standard cosmology predicts and what astronomers actually observe surrounding us. The void's emptiness is not primarily an illusion created by hidden galaxies lurking behind cosmic dust. The vast majority of the missing mass genuinely appears to be absent, not simply hard to see. This matters enormously for how seriously scientists take the entire void hypothesis. If the emptiness had turned out to be mostly an observational illusion, an artifact of galaxies hiding behind dust and poor sensitivity, the entire foundation connecting our void to the Hubble tension would collapse instantly. Instead, careful searching has reinforced the opposite conclusion. Our neighborhood really is unusually empty, confirmed both by counting what we can see and by actively searching for what might be hidden. largely coming up empty-handed in that search too. That empty-handed search, in its own strange way, carries more scientific weight than a successful one might have. A negative result, achieved through genuinely rigorous effort, closes off the easiest possible objection to the entire void hypothesis, forcing skeptics to look elsewhere for reasons to doubt it, and forcing everyone else to take the emptiness surrounding us just a little more seriously than before. The handful of dwarf galaxies that were found tell their own small story. Most sit far from the void's presumed center, clinging closer to its edges where faint gravitational influence from the denser walls outside still lingers. None have been found deep in the emptiest heart of the region, exactly where the standard model would predict the fewest galaxies of all, if the void's underlying density profile is as extreme as current measurements suggest. Every mystery in this story eventually runs into the same limitation: the quality and reach of the instruments available to test it. For decades, testing the void hypothesis meant working with survey data collected for other purposes, pieced together after the fact. Useful, but never quite comprehensive enough to fully settle the argument. That situation is finally beginning to change, and the shift matters more than a simple upgrade in equipment might suggest. New generations of astronomical surveys, built specifically to map the three-dimensional structure of the universe with extraordinary precision, are now actively collecting the exact kind of data this mystery has needed for years. These projects are designed to measure the positions and velocities of tens of millions of galaxies across enormous stretches of sky, creating maps detailed enough to trace the precise boundaries, depth, and shape of structures like the KBC void, with a level of confidence earlier researchers could only dream about. To appreciate how much has changed, compare this to the original discovery decades ago, when researchers plotted a few thousand galaxies painstakingly, one measurement at a time, using instruments that took entire nights to gather data. Modern telescopes can now collect in minutes. Today's surveys operate closer to an assembly line, automated systems capturing the light of thousands of galaxies simultaneously, building three-dimensional maps at a pace earlier generations of astronomers would have considered pure fantasy. One particularly powerful technique involves measuring what scientists call peculiar velocities, the small extra motions galaxies exhibit beyond the universe's overall expansion, motion caused specifically by nearby gravitational influences like voids and clusters. By carefully mapping these peculiar velocities across thousands of galaxies near our void's boundary, researchers can directly test whether galaxies are moving in the specific outward pattern predicted by the void outflow hypothesis, rather than relying only on indirect galaxy counting methods used in earlier decades. These modern surveys also benefit enormously from combining multiple independent distance measurement techniques within the same dataset, comparing results from supernovae, from galaxy rotation speeds, and from the frozen ripples of baryon acoustic oscillations left over from the early universe. Each individual technique carries its own particular weaknesses, its own assumptions that could quietly bias a result in one direction or another. Where earlier studies often relied on just one or two of these methods, creating room for lingering doubt, newer surveys can cross-check results across several independent techniques simultaneously, dramatically narrowing the uncertainty surrounding the void's true depth and influence. For the first time in this decades-long investigation, scientists are not simply waiting for better data to arrive someday. They are actively collecting it right now, running the exact tests this mystery has always needed, using instruments precise enough to finally distinguish between competing explanations that earlier generations of astronomers could only argue about using incomplete evidence. The answer, once scattered across dozens of separate studies and simulations, is finally converging towards something closer to certainty. Researchers involved in these projects describe an unusual sense of anticipation, rarely felt this strongly in a field, often measured in decades rather than years. For the first time since Kirshner stumbled onto the Boats void back in 1981, scientists studying cosmic voids have a genuine, realistic timeline for resolving one of the field's oldest open questions, rather than simply adding another inconclusive study to an already crowded pile. Imagine the moment, likely arriving within the next decade, when astronomers finally settle this question with enough confidence to stop calling it a hypothesis. What would that resolution actually mean for how humanity understands the universe, beyond simply satisfying scientific curiosity about one unusually empty patch of cosmic geography? Three broad outcomes remain realistically on the table, and each one carries genuinely different consequences worth considering separately, each reshaping the conversation in its own distinct way. If it turns out the KBC void fully explains the Hubble tension, the implications ripple outward in genuinely exciting directions. It would mean the standard model of cosmology, battle-tested and successful in countless other areas, does not need dramatic new physics to explain one of its most stubborn anomalies. It would mean the universe, at the largest scales, behaves exactly as predicted, and the entire crisis was ultimately a story about geography rather than broken physics, a reminder that where you stand can change what you measure, even when the underlying laws remain untouched. This outcome would carry a certain satisfying elegance. Decades of anxious debate, entire conferences dedicated to rescuing the standard model from an apparent crisis, would resolve into a single, almost humbling explanation. We simply forgot to account for exactly where our own telescopes happened to be sitting. No exotic particles required, no rewriting of fundamental physics, just a careful correction for local geography, applied consistently across every measurement that needed it, quietly resolving a decade of anxiety. If instead, the void only partially explains the tension, leaving a meaningful gap still unaccounted for, the implications shift in a different, arguably more thrilling direction. It would mean something genuinely new remains hidden in the standard model, some ingredient or mechanism not yet fully understood, waiting to be discovered by whichever research team manages to isolate exactly how much of the tension the void can and cannot explain. Far from disappointing, this outcome would hand physicists an entirely new frontier to explore. And if, against most current expectations, the void turns out to have little meaningful connection to the tension at all, that outcome would carry its own significance. It would mean the Hubble tension remains a genuine, unresolved mystery, forcing scientists back toward more exotic explanations involving new particles, modified gravity, or entirely unknown physics operating in the early universe. Even a disappointing result, ruling out our void as the culprit, would meaningfully narrow the field of remaining suspects, saving future researchers from chasing a lead that never would have panned out. Every possible outcome, in other words, moves science forward. This is worth remembering whenever a mystery like this feels frustratingly unresolved. Uncertainty is not evidence of scientific failure. It is evidence of scientific work still actively happening, moving steadily toward an answer that will matter no matter which direction it ultimately points, and worth watching closely as new results continue arriving. Whichever outcome eventually arrives, one thing seems increasingly certain already. The days of treating our own cosmic neighborhood as a boring, irrelevant footnote to the real work of studying distant, exotic corners of the universe are effectively over. The empty space surrounding our own galaxy has earned a permanent, central place in one of the biggest open investigations in all of modern physics. Step back for a moment and consider something almost dizzying buried inside this entire investigation. Every measurement scientists use to study our local void, and every supernova used to calculate the Hubble constant, relies on light that began its journey toward Earth long before humans existed to receive it, sometimes billions of years before our own solar system had even formed. This detail adds a layer of genuine wonder to an otherwise highly technical scientific debate. When astronomers study a supernova exploding somewhere near the edge of our void, they are not watching an event happening today. They are watching light released potentially hundreds of millions of years ago, a flash of destruction that occurred long before dinosaurs walked the Earth, only now completing its long journey across the emptiness separating us from that distant point in the cosmic web. Every measurement discussed throughout this entire investigation carries this same built-in time delay, layered on top of every other source of uncertainty already covered. Scientists work with imperfect instruments and contested statistics, and also with information that is, by its very nature, always describing a version of the universe that no longer exists exactly as observed, changed subtly, and sometimes not so subtly, in every moment since that particular beam of light first departed on its long journey toward Earth. This means our entire picture of the void surrounding us is, in a strange sense, a picture of the past rather than the present. The void as it exists today, this very moment, right now, is almost certainly larger and emptier than anything astronomers have directly measured, simply because dark energy has continued stretching it wider during all the time it took that ancient light to finally reach our telescopes. We are studying a snapshot, not a live broadcast, piecing together the history of an ever-changing structure using fragments of light frozen at the moment they departed their distant sources. This same principle applies with even greater force to the cosmic microwave background discussed earlier. Light that began traveling toward us before galaxies, before stars, before almost everything familiar in the modern universe had even formed. Every measurement in this entire story, from the freshest supernova to the most ancient background radiation, arrives carrying a delay, a built-in time capsule effect that scientists must carefully account for whenever comparing measurements taken from wildly different points in cosmic history. Understanding this delay reshapes how we should picture our place inside this story entirely, far beyond a simple technical footnote. We are not simply residents of an unusually empty region of space. We are observers, piecing together an incomplete flipbook of that region's history, using fragments of light arriving from wildly different moments in time, attempting to reconstruct where we are and when. In the truest sense, everything we are looking at actually happened. There is something quietly poetic buried inside this technical detail. Every galaxy visible in the night sky is, in a sense, a ghost, a faithful record of light released long ago by an object that has since continued evolving, moving, and changing in ways we cannot directly witness. Studying the universe has always meant studying its past, layer upon layer of delayed messages arriving from every direction, and our own local void is no exception. Its true present-day shape forever hidden just slightly out of reach behind the finite speed of light itself. After everything covered so far, one final, deeper question remains stubbornly unresolved, a question sitting beneath all the specific technical debates about density measurements, standard deviations, and competing survey results. Why does a void this large, this empty, and this suspiciously well-positioned near our own galaxy actually exist in the first place? Standard cosmology offers a reasonably satisfying explanation for smaller, more typical voids. Tiny fluctuations in the density of matter, present from the earliest moments after the Big Bang, naturally grew over billions of years into the underdense regions we observe scattered throughout the cosmic web today. Gravity amplified small initial differences, pulling matter away from slightly emptier regions and towards slightly denser ones, carving voids and filaments out of what began as a nearly, but not perfectly, uniform universe. This explanation works well for the vast majority of voids astronomers have catalogued. Structures within the size range predicted comfortably by standard theory, appearing at roughly the frequency simulations expect across a randomly sampled universe. It is only when a void grows dramatically larger than that typical range, as ours appears to have done, that the standard explanation begins to strain under its own weight. But this explanation strains considerably when applied to something the size of the KBC void. Earlier in this story, researchers calculated that finding ourselves inside a void this large and this deep, purely through the ordinary process of gravitational amplification predicted by standard theory, would happen at odds exceeding 6 standard deviations against expectation. That number represents genuine tension between observation and theory, not a settled explanation quietly waiting to be confirmed. Some researchers have proposed that our void might trace back to something unusual happening in the earliest fractions of a second after the Big Bang, during a period called inflation, when the universe expanded from something smaller than an atom to something astronomically vast in an instant almost too brief to measure. Under certain specialized models, different regions of the universe could have followed slightly different inflationary paths, creating occasional large-scale variations in density baked directly into the fabric of space, before galaxies, before stars, before anything familiar existed at all. This remains genuinely speculative territory, discussed seriously by specialists but far from confirmed by hard evidence. It sits at the frontier where cosmology brushes up against some of the deepest unanswered questions in all of physics. Questions about the very first moments of existence, questions current instruments are only beginning to develop the sensitivity to properly test. Whatever the true answer turns out to be, it may reveal something fundamental about how the entire structure of the universe was written into existence, far beyond simply explaining our own void in the impossibly brief moment before anything we recognize today had even begun to take shape. It is a strange thought to sit with. The reason our night sky looks the way it does, the reason certain measurements taken from Earth disagree with measurements taken from the ancient light of the Big Bang, might trace back to something that happened in a fraction of a second, at the very beginning of time itself, long before galaxy formation or anything else recent in cosmic history, before the universe had cooled enough to form a single atom. If our own galaxy happens to sit inside one unusually empty region, a natural question follows almost immediately. How many other galaxies, scattered across the observable universe, might be sitting inside similarly unusual neighborhoods of their own, dense clusters, empty voids, or something in between, each one quietly shaping how an alien astronomer on some distant world might measure and interpret their own corner of the cosmos? This question turns our entire story into something bigger than a single local mystery. If voids covering roughly 80% of the universe's volume host galaxies at all, and evidence suggests many contain at least scattered dwarf galaxies, then a meaningful fraction of all galaxies in existence may be experiencing something similar to what we experience here. An underdense neighborhood, subtly distorting local measurements of cosmic expansion, just as ours appears to be doing for us. Consider the sheer scale involved. Cosmologists estimate the observable universe contains somewhere on the order of hundreds of billions of galaxies, scattered across a cosmic web woven from voids, filaments, walls, and clusters. If a meaningful fraction of those galaxies sit inside voids of their own, then any hypothetical astronomers living there would be conducting their own version of exactly this investigation, wondering why their local measurements of cosmic expansion do not quite match the ancient, universal light arriving from every direction. Consider, briefly, what science might look like from inside a galaxy sitting near the crowded core of a massive galaxy cluster instead, surrounded by thousands of close neighbors rather than a comparative handful. Astronomers there might face a nearly opposite challenge: an overabundance of nearby gravitational influences complicating their measurements in different, equally frustrating ways. Just as our own emptiness complicates ours, their supernovae readings might carry a bias pulling in the opposite direction from ours, requiring their own careful corrections before trusting any conclusion about the wider cosmos. This turns our specific cosmic address, one particular void among many scattered throughout an unimaginably vast universe, into a useful case study for a much broader scientific principle. No single vantage point anywhere in the cosmos offers a perfectly neutral, unbiased view of everything else. Every observer, wherever they happen to arise, inherits the specific advantages and specific blind spots baked into their own particular corner of cosmic structure whether that corner sits deep inside a crowded filament or deep inside an empty void like ours. Recognizing this pattern does not diminish the value of what we have learned studying our own neighborhood. If anything, it enhances it. Our void becomes a working example, close enough to study in exceptional detail, of a challenge every intelligent observer anywhere in the universe would eventually need to confront. Understanding exactly how standing somewhere shapes and potentially distorts everything you think you have learned, not simply what you can measure from where you stand. This turns the entire investigation from a purely local story into something closer to a universal principle, discovered first here, in our own cosmic backyard, but applicable everywhere structure exists. Wherever intelligent life eventually arises across this vast, web-like universe, it will face some version of the exact same lesson our own astronomers have spent decades learning, that understanding the whole requires first understanding and correcting for the specific and unrepeatable vantage point from which you happen to be looking. There is a particular kind of discomfort built into everything this investigation has uncovered, one worth naming directly rather than glossing over. Science generally prefers clean, confirmed answers over open, contested uncertainty. Yet almost everything covered across this entire story remains genuinely unsettled, argued over by serious, careful researchers who disagree with each other in good faith, using the same data to reach meaningfully different conclusions. This sits at the very center of the story, far from a flaw hiding at the edges of an otherwise finished picture. Is our void deep enough to fully explain the Hubble tension, or only partially? Does the cold spot trace back to a supervoid, or does it represent something stranger still unexplained? Does dark energy's disproportionate influence inside voids represent ordinary physics playing out exactly as expected, or a genuine crack in the standard model waiting to be more fully understood? None of these questions currently have a single, universally agreed upon answer. Even among researchers who broadly agree on the raw data, disagreements persist about interpretation, about which statistical methods deserve the most trust, about how conservatively or aggressively to extrapolate from limited samples towards sweeping conclusions about the entire universe. This is evidence of a field taking its own claims seriously enough to argue over every detail before declaring anything settled, rather than a field in disarray. Good science tolerates this kind of extended uncertainty far better than casual intuition typically expects it to. Outside of careful research, people often assume science works by delivering quick, confident, permanent answers, settled once and reported cleanly in a textbook forever after. Real frontier science looks like exactly what this story has traced: careful measurement, competing interpretations, slow building evidence, genuine disagreement among experts, and patient, incremental progress towards something closer to certainty, arriving piece by piece, survey by survey, decade by decade, rather than all at once. There is a kind of intellectual humility required to sit comfortably inside that uncertainty without either dismissing it entirely or overselling premature conclusions in either direction. The KBC void almost certainly exists. That much rests on solid, repeatedly confirmed observational ground. Exactly what it explains, and exactly how deeply it reshapes our understanding of measurements taken from Earth, remains an open, actively contested question, one honest scientists readily admit they cannot fully answer yet. That honesty is not a weakness in the story we have been tracing. It is the story's greatest strength. A universe this large, studied by observers confined to one single, specific vantage point, was never going to yield its deepest secrets quickly or completely. What we have instead is something more valuable than false certainty, a genuinely rigorous, ongoing investigation, inching closer to the truth, using exactly the kind of careful, patient, self-correcting process that has always defined science at its very best. Every generation of astronomers before us believed, at some point, that they had finally mapped the universe correctly, only to have the next generation gently, respectfully, and evidentially prove them wrong in some meaningful way. There is no reason to expect the current generation to be any different, and there is no shame whatsoever in that pattern continuing. It is, in fact, exactly how a field built on genuine curiosity is supposed to behave, forever willing to update its picture of reality as better evidence arrives. Consider, for a final moment, just how strange and specific our exact cosmic address actually is. Once every piece of this investigation is placed side by side, we do not simply live on an ordinary planet, orbiting an ordinary star inside an ordinary galaxy. We live deep inside one of the largest, emptiest structures cosmologists have ever mapped, a void stretching roughly 2 billion light-years across, sitting closer to its underdense core than its crowded edge. Statistically, this places us somewhere genuinely unusual compared to a typical randomly chosen location across the observable universe. Most galaxies, sitting along the cosmic web's crowded filaments and clustered nodes, would never experience anything close to the kind of local emptiness surrounding our own Milky Way. We are not average. We are, by the numbers researchers have calculated, closer to a statistical outlier, an unusual result sitting several standard deviations away from what most models of cosmic structure would predict as typical. There is a strange comfort hidden inside that fact. Once you sit with it long enough, being unusual does not mean being wrong, damaged, or somehow lesser. It simply means being rare, occupying a genuinely uncommon address inside a universe built overwhelmingly from crowded filaments and dense clusters. Just as a lighthouse standing alone on a remote stretch of coastline is no less real or valid than a building packed into the middle of a busy city, our galaxy's unusual position inside this vast emptiness does not make it any less a genuine, fully formed part of the wider cosmos. There is something worth pausing on in that fact, beyond its technical implications for measuring the Hubble constant. Every civilization capable of building telescopes and asking these exact questions has to begin from wherever it happens to arise, with no ability to relocate somewhere more statistically convenient before starting its investigation. We began here, inside this particular void, and every single insight humanity has ever gathered about the wider universe has been filtered, at least partially, through the unusual geometry of this specific cosmic neighborhood. This should inspire a certain quiet admiration for how much scientists have managed to piece together correctly, despite observing everything from inside a genuinely atypical vantage point, rather than despair about the reliability of human knowledge. The fact that researchers can even detect, measure, and seriously debate the void's influence at all, rather than remaining completely unaware of it, demonstrates the remarkable power of careful, patient, cross-checked observation to overcome exactly the kind of local bias this story has spent so long tracing. We are, in the truest sense, residents of a rare address inside an almost incomprehensibly vast universe, standing in a spot few other galaxies occupy, looking outward through a lens subtly shaped by the emptiness surrounding us. Understanding that lens, rather than ignoring it, may turn out to be one of the most important scientific achievements of this entire era, a project still very much unfinished and still very much unfolding. Every telescope pointed skyward, every survey mapping distant galaxies, every careful calculation of the Hubble constant adds one more small piece to that unfinished project, slowly sharpening humanity's picture of exactly where and exactly how, unusually, we happen to be standing inside this vast, structured cosmos we call home. Every thread in this investigation eventually leads back to the same central realization. The place you stand shapes what you can see, and shapes how confidently you can trust what you understand about everything beyond it. We began this story looking up at a sky that felt crowded, full, endless. We end it understanding that sky differently, as a view filtered through the unusual geometry of one of the emptiest regions ever mapped in the observable universe. None of this diminishes the extraordinary achievement modern cosmology represents. Scientists did not simply accept a comfortable assumption that our neighborhood looked typical and stop investigating. They noticed a subtle discrepancy in careful measurements, chased that discrepancy across multiple independent surveys and instruments, built simulations to test whether chance alone could explain it, and are now actively refining precise tools capable of finally settling the question with genuine confidence. That entire process, messy, contested, and still unfinished, represents science functioning exactly as it should. Think back to where this story began, with a single blank patch of sky noticed almost by accident in 1981, dismissed at first as a possible equipment failure. That small, uncertain observation eventually grew, decade by decade, survey by survey, into one of the most consequential open questions in modern physics, touching everything from the age of the universe to the ultimate fate of the cosmic web itself. What remains genuinely uncertain, and worth carrying forward honestly rather than glossing over, is exactly how much of the Hubble tension our local void explains, whether the cold spot truly connects to a distant supervoid or represents something else entirely, and whether the accelerated growth of empty regions under dark energy will eventually be fully confirmed as the dominant force reshaping the universe's deep future. These questions remain open, actively studied, and likely to be meaningfully clarified within the coming decade as new surveys finish gathering their data. What is not uncertain is the underlying shape of the story itself. We live inside an enormous, confirmed void, one of the emptiest and largest structures cosmologists have ever mapped, and that fact alone has already reshaped how seriously scientists question assumptions once taken for granted about our place in the cosmos. Every distance calculated, every age estimated, every claim made about the size and structure of everything beyond our galaxy now carries an added layer of careful scrutiny, thanks to this one persistent, patiently investigated anomaly. Look up again, sometime, on a clear night, away from city lights. The sky will still look crowded, full, endless, exactly as it always has. But you now know something most people never stop to consider. That feeling of fullness is, in a very real sense, an illusion created by proximity, by a handful of relatively close, relatively bright galaxies scattered across an otherwise strikingly empty stretch of cosmic geography. Somewhere beyond what your eyes can detect, the true architecture of the universe continues. Filaments and walls and clusters, and vast canyons of nothing stretching for hundreds of millions of light-years in every direction, quietly shaping every number scientists have ever calculated about the universe we call home. That is the quiet, extraordinary truth behind one of the most contested numbers in modern science. Not a flaw in the universe, not a flaw in our instruments. Simply the honest fact that we live somewhere unusual, inside a hole in the cosmic web large enough to bend our view of everything beyond it, and brave enough scientists spent decades learning to see clearly, one careful measurement at a time.